Welcome to the solution video for the puzzle which was published on March 14th of 2024, and it was called Cherries. And it was called Cherries because it shows two circles, not necessarily of equal radius, and two tangents. They are shown in green and they are intersecting, and those two tangents, those line segments are of equal length. And there is a third line, blue line segment from the intersection point to the tangency point of the two circles. And we are asked to prove that this blue line is actually a common tangent of both two circles. And to prove that, I have received several ones, and more or less always boils down to a proof by ad absurdum. So you suppose something and you come to a contradiction. So I will take a slightly different approach. I will also use this technique, but what I will do is I will use the power of a point theorem. And what I will do is that first of all I will assume that this is not a tangent. And what does that mean? I will assume that it has, there is one intersection point if it is a tangent, but if it is not, it has two intersection points with the circles. So if I, let's suppose that this line is the blue line. Well, to make it even more apparent, look like this. Well, then there are indeed two intersection points with the smaller circle and also two with the larger circle. And I will show that in fact there cannot be those two other intersection points. It's more like an algebraic approach. Let's first of all name the length of the green segments A. They have both length A. Let's name this part of this vertex to the smaller circle. Let's name that B. Let's name the chord inside the smaller circle C, and the chord inside the larger circle, let's say it has length D. And that's all we need to prove it. Well, first of all, I'm going to take the power of a point of this point G, which is the intersection, to first of all the power of a point with respect to the smaller circle. Well, you can do that in two ways. You can use the tangents, and then you know that power of a point is the square of that tangent. So we have that a squared, that's the power of the point, but it is also equal to b times b plus c. That's the power of a point theorem. So that's a first equation we have. It is b times b plus c. That's the power of a point of this g with respect to the smaller circle, and that's a squared. But now we're going to take the power of a point of the same one with respect to the larger circle. It's also because the tangent has length a, so it is also a squared. But now it is the distance to the circle, which is b plus c, to the large circle, b plus c, times the total distance to the second intersection, so that's b plus c plus d. b plus c plus d. Those are the same. Okay. So we have two equations. Well, obviously what we're going to do is to get rid of the a squared. So we equate them. We have b times b plus c equals b plus c times b plus c plus d. It's very easy. Now what we do is left and right we have two b squared terms. Well, we can get rid of those, and we have two bc terms, so we can get rid of that one too. So what we have is that bc plus bd plus, well, the bc is dropped, plus c squared plus cd. If I have done it correctly, that should be 0. So that's basic factoring out. Yes. So let's see if I've, well, that's apparently that's not correct. So it cannot be bc. It's b c. Okay, oh no, that's correct. There are two BC terms, so this is indeed is correct. So if I rewrite that, let's say let's factor out the c's. We have b plus c plus d plus, and then we are left with bd. Oh, that's very basic. Okay. What we're going to use now is that b definitely is larger than 0, because there is a certain distance to the circles. So b is larger than 0, and we have here two terms which are all positive numbers, so, and they should add up to 0. But that means is that the second term bd is 0, and because b is 0, we have found that d is 0. 0, like this. That's the first result. But now we're going to look at that term, and because b is not 0, d is 0, we have that c squared is 0, therefore we have that also c is 0. But hey, that's very interesting. We have just proved that the distance between those two intersection points is 0, so that basically means they are the same, they coincide. And the distance between those two intersection points is also 0, they also coincide. So what we basically now have shown is that the blue line has only one intersection point with both circles, and therefore it must be the common tangent. And so we have used the ad absurdum technique to show that the blue line is the common tangent of the two red circles.